So gas particles travel in a straight line until they run into something. The distance, the average distance that they can travel without running into something is called the average free path, or the mean free path. That mean free path is going to decrease as the pressure increases, because when the pressure increases, the particles are closer together and they're going to run into each other more. They're running into each other more because, that's why the pressure's higher, is because they're running into each other more. Yeah.
Is there a temperature, I feel like there's a temperature at which a substance is no longer a gas?
Yes, that's true.
Because I just thought about it, if you have 0 degrees Kelvin, then the whole thing, you can't have something at 0 degrees Kelvin, right?
Right.
Because then the whole equation is just 0.
Right, so at 0 Kelvin, which is absolute 0, the ideal gas law would predict that the volume is 0. Well, if n is something other than 0, the volume can't be 0. But the thing is, when you take a gas and you cool it down, at some point it's going to condense into a liquid. And then it's not a gas anymore, and the ideal gas law doesn't work for it.
So that's why when you showed us that chart, it was just there was a point where it had stopped, and then it was just stopped.
Yeah, so we had that graph where we extrapolated the data and it all intersected at 0 Kelvin. But the data stopped at 0 Celsius, because whatever gas it was then no longer a gas at lower temperature, and so you can't measure it. And so we're going to talk about some aspects of that in just a minute. Just as an example here, in nitrogen, which is the main component of air, if nitrogen was the size of a golf ball, it would travel about 40 feet between collisions. So there's quite a bit of travel time here without colliding. And this is just illustrating, here we've got this particle, and it bounces off the wall, and then it goes over here and hits something else. And so you can trace its path here, and the average length of these lines would be the mean free path. Mm-hmm.
So if you put your hand through steam,
Mm-hmm.
you can feel it because there's more collisions in there? It's more dense?
When you put your hand through steam, a lot of what you're feeling is that when those gas particles hit your hand, they condense and they release heat into your hand. So there's several different factors going on in there. And there's probably some density issues as well. Diffusion and effusion. So these are two terms that could show up. Let's see, do you know the difference? Do you know what these things are? Diffusion is the process by which gas molecules spread out from high concentration to low concentration. So diffusion is how when someone farts in the corner and it's really stinky, the stink gets everywhere, right? Because it's going from a high concentration, where the person who dealt it was, and it spreads out until everyone can smell it. Right? That's diffusion. And then effusion is the process by which a gas escapes through a small hole into a vacuum. The rates of both of these are related to the root mean square average velocity. So at the same temperature, the rate of gas movement is different, right? So small particles are moving fast and large particles are moving slow. And so the rates of diffusion and effusion are going to be different based on the size of the particles because their average velocities are different. Mm-hmm. Well, I gave you an example of diffusion. Oh, effusion. Yes, I'm going to talk about effusion right now. Those words are so similar. So here is an illustration of effusion. So here we have a box that's divided into two parts. And originally there's gas on one side and there's nothing of vacuum on the other side. There's a small hole here. Now when we think about pressures and vacuums and sucking things through holes, it seems different than what it is on the particulate level. So this is a pressure. You could think of this as being like a balloon or a car tire, and you put a hole in it, right? So what's going to happen? The gas is going to come out, right? But exactly how does that gas come out? Well, these particles here are just doing their particle thing, and they're just being pong blips, and they're traveling in straight lines till they run into something, and then they bounce off and they go again. And they're only going to escape through this hole if they are on a course that runs them directly into the hole. Otherwise, they're just going to keep bouncing around. And so how fast a particle or how fast a gas sample gets through this hole is going to depend on how fast the particles are moving. Because if these are moving fast, they're bouncing around, and every time they're bouncing around, they have a chance at hitting that hole. They have more chances of hitting the hole. If they're moving really slowly, they're going to hit the hole less frequently. It's going to take them longer.
So if the hole isn't big enough now, like say the hole is too small for the particles to go through, like they won't escape.
Right. If the hole is too small, they won't escape. But we're assuming the hole is large enough. Yes?
Is that like the principle of osmosis then?
Is that like the principle of osmosis?
The only reason why I ask that is because there's definitely, like even in solids, there's small space between atoms, right? And so like if that space is large enough for an atom to pass through, could they go through it?
Yes, they could. There are some similarities, and we're going to talk about osmosis later, and talk about it's really an equilibrium process, but it does involve it is similar to this in some ways. Because what about these particles? Once we get particles on the other side, could they come back?
Yes.
Sure, they could. If they happen to hit the hole, they could come back.
It's just a lot less likely.
It's less likely because like there's only 3 particles over here and there's a whole bunch over there. And so it's much more likely that particles from this side are going to go that way. And so that does have similarities to osmosis. This is also what happens when balloons lose their gas, right? And so if you blow up 2 identical balloons and you put helium in one and you put air in the other and you wait, the helium balloon will shrink faster than the air balloon. And it's not because the helium atoms are smaller than the nitrogen atoms, which they are. The holes in the latex are big enough for both of them to go through. Otherwise, the air balloon would never go flat. But the helium atoms are smaller, and so at the same temperature, they're moving faster. And so they will effuse faster than the air molecules. So we can put the root mean square equation, we can combine 2 of those and we can get this relationship. This is called Graham's law of effusion. And again, I'll give you this equation, but there will probably be a problem where you have to use it. The rate of effusion is inversely proportional to the square root of the molar mass. So the rate of A effusing to the rate of B is equal to the square root of the molar mass of B over the molar mass of A. So the larger particle effuses more slowly. So let's do an example. Find the ratio of the effusion rate of hydrogen gas to that of krypton gas. So what we want here is we want the ratio, the rate of hydrogen to the rate of krypton. The words are telling me the order. hydrogen to krypton. So I can use Graham's law of effusion, and that's the square root of the molar mass of krypton divided by the molar mass of hydrogen. Coming from that root mean square equation, these molar masses were in kilograms per mole. Here, because we're doing a ratio, you can put them in kilograms, but you can also have them in grams because all of the units cancel out, and so it doesn't matter. So the square root of the molar mass of krypton, 80, it's a bad reflection up there, 83.80 grams per mole, divided by the molar mass of hydrogen, which is diatomic, 2.016 grams per mole, the square root. So that diatomic business, I'm not necessarily trying to trick you with a question like this, hydrogen gas, but that's something you need to be aware of. If it says hydrogen gas, nitrogen, oxygen, any of those diatomic elements, the formula is got a 2 in it, and that changes the answer because it's H2. So the molar mass is different. So the square root of 83.8 divided by 2.016, 6.447. And those units cancel out. There's no units here because it's a ratio. You might say, well, that's not a ratio, that's a single number. Well, it's that over 1. 6.447 to 1. So hydrogen will effuse 6.447 times faster than krypton. Any questions?
So do you want that as, like, do you want the 1 under there? I mean, it's obvious because it's like, that's a number over 1.
Right. This would probably be a multiple choice question.
Okay.
And so how exactly the answers were displayed might vary, but I just want to point that out so that if it shows you an answer of 6.447 colon 1, and you come up with a number 6.447, it means the same thing, but it's not necessarily obvious that it means the same thing.